Next we will perform delete min operation. First we are having number of keys. Let these be the keys which we have to arrange first in the form of binomial heap, and then from these keys we have to delete the minimum value. So first arrange them in the form of binomial heap. After getting to B0, again we are supposed to have 1 B1, then 3 will come, then 4 will come, one more B1 will be there, 2 B1 again. We can arrange them to have a B2, again to B0, we will get 1 B1, the last one is 7. These are the keys which we are supposed to have in the form of binomial tree in our binary heap. First we will find the minimum. Now again from here you can find, to find the minimum in the binary heap we are just supposed to find the min heap top value or the root value, that is having the complexity, worst case complexity big O1, because in the one time instant we are supposed to get the value. But in this given binomial heap, if I want minimum value, find minimum value, I have to trace all the trees, first binomial tree, second binomial tree, third binomial tree, and from there only I can conclude okay, which one is having minimum root value. So again the complexity for finding the minimum is number of trees, and number of trees is log n. So for find min, the complexity will be number of trees, worst case complexity, and these number of trees, since we are calculating the number of trees from the binary conversion of the given number of keys, so we can say it is log n. Now we are having this binomial heap. I want to delete the minimum. I had find the minimum, that is 1 after tracing all the trees. Now I want to delete this minimum value 1. After deletion or extracting this minimum value, the resultant will be these binomial trees. So after deleting the minimum, whatever the resultant binomial trees or left binomial trees, you have to perform merging of them. So we are having here 2b1 and 2b0. So after performing the merging, we are having this binomial heap. We can prove again, we are having 7 keys here initially. The binary conversion of this 7 is B0, B1, B2. All the trees are present in the binomial heap. After deleting one value, we are left with 6 keys. And the binary conversion for 6 is 1, 1, 0. So, no B0, B1 and B2 are present in the resultant binomial heap. This is one B1, this is B2. Again, for deletion operation, when I find the minimum value and then it will be removed from the binomial tree, okay, we are left with these binomial tree which we have to merge, organize them in the higher order binomial trees and put in the heap. So again it will be dependent upon the number of trees, and number of trees is equivalent to the log n. So the complexity again for delete min will be worst case complexity big O log n, which is in the binary heap big O 1, because the min heap is lying at the top. So, I summarize the topic. We had gone through binary heap, the usage of the binary heap or the binomial in the Fibonacci heap is to find or to solve the algorithm which are having certain priority constraint. For example, if we require to schedule certain job according to their shortest time, there we require this heap concept. Second, if we want to find shortest path in the minimum spanning shortest tree, there again we are supposed to use these heap concept. Again in A star algorithm we are using the heap concept. In the binary heap we had discussed it is of two types, min heap, max heap, depending upon the property they are following. If it is min heap, then the value at the root or the parent is having smaller value as compared to its child node or equal value, while if it is a max heap, then the parent is supposed to have maximum value or greater value or equal value as compared to its child node, followed by certain operation for the binary heap. Making of the heap, always it is having big O 1 complexity, because we are creating an empty heap with 0 nodes or 0 trees. So, the complexity worst case will be big O 1. When we insert an element in a heap, the heapify operation will be called, and that is supposed to propagate from the leaf node to the root node. The complexity will be big O log n. For finding of minimum or finding of maximum element from the binary heap, always the complexity remain big O 1, because the root is having min element in case of min heap and max element in case of max heap. If we want to delete the minimum element, again we have to remove it from the root, and that will be replaced by the leaf value, and again the heapify will be called, that is having the complexity big O log n. After binary heap, we go to the binomial heap. We tell that binomial heap is the composition of binomial trees, ordered binomial trees, and again the binomial trees are having 5 properties. One by one I repeat. Binomial trees, if I am representing it by bk, k stands for the order of tree. This tree is having k degree. Second property, it is having height k. The number of nodes present in this tree is 2 to the power k. The fourth property, the number of nodes present at particular level I is calculated by the formula NCI, that is equals to n factorial, sorry it is here k factorial, I factorial, k minus I factorial. And the last property, every binomial tree is a composition of 2 binomial tree of order 1 less than it. After making different order binomial trees, we had performed certain operation on the binomial tree. Basically, binomial heap is used, or it is performing efficiently the union operation of binomial trees. So, we had studied all the insertion, increase of element, deletion of the element, and merging of 2 heaps. Hello everybody, I welcome you in the next session. In the previous section, we had completed binary heap and the binomial heap. Now we will study Fibonacci heap. I told you that binomial heap, it is a collection of ordered binomial tree. Performing efficient union of operation. Instead of collection of ordered binomial tree, Fibonacci heap, it is a collection of unordered binomial tree. Now what we mean by unordered binomial tree? Fibonacci heap, it is a collection of unordered binomial By unordered, we means, as in binomial tree, I had already told you that in a particular binomial heap, we are supposed to have unique ordered tree. As soon as we get same ordered tree, we will perform merging of them. Either while merging, we will merge at the left side, two binomial tree are merged in the order, either they will be attached as a left child or as a right child, that will be followed in the whole heap. While in Fibonacci heap, we are supposed to have such a heap, we can have same order tree Second thing, the order of merging is not necessary same. You can have in the heap B2 like this, B2 like this. It can be at the left side, it can be at the right side, no constraint is there. Again, the unordered binomial tree, the number of nodes present in it is 2 to the power k. The degree of unordered binomial tree is again k. The number of nodes present in unordered binomial tree at a particular level is again NCI, that is n factorial divided by c factorial n minus I factorial. I can write the properties here. Number of nodes present is 2 to the power k is k, degree of bk is k, number of nodes at level I is KCI equals to k factorial I factorial k minus I factorial. Fourth and very important property which distinguish unordered binomial tree from ordered binomial tree is unordered binomial tree Bk is composed of Bk minus 1, Bk minus 2, Bk minus 3 in unordered manner. So, a Fibonacci heap is a collection of unordered binomial tree. What is an unordered binomial tree? It is same as your ordered binomial tree, only the order is not mattered here. You are not supposed to arrange the nodes or binomial tree to get the higher order binomial tree in a particular order. You can add at the left side, right side, in between, whatever. For Fibonacci heap, we are having one more property, or we can say potential method is defined for a Fibonacci heap. Represented by phi h. This potential method will be used for amortized analysis of the Fibonacci heap. The reason for performing amortization or amortized analysis is it is supposed to be performed for the data structures where for every operation the complexity is not large, or we can say there is a large variation of complexity for different operation. So, if we want to say that if we are using this particular data structure, we are calculating the average complexity, it is not good, because a particular data structure should be used for particular operation. Okay. So, we are performing amortized analysis. We are calculating the complexity for peculiar operations, and this potential method, we are having three different methods to calculate to perform amortized analysis. First one is our aggregate method, in which all the operations worst case complexity will be calculated, that will be added and divided by the number of operations, and then we can tell that this is the amortized complexity calculated by aggregate method for a particular operation. In the potential method, we are having the calculation here. It is equals to number of trees present in the Fibonacci heap plus twice of marked node present in the Fibonacci heap. This potential method is something related with the potential energy. The energy, if initially it will be not consumed, it will be retained and it will be utilized for the further operations. So, this is the method to calculate the, I am not going in detail because right now I am discussing the topic of Fibonacci heap. Just I am telling you what is the potential method. It is a part of amortization analysis, and this will be calculated for the Fibonacci heap. Number of trees present in the Fibonacci heap twice the number of marked node present in the Fibonacci heap. Now, we will perform different operation on the Fibonacci heap one by one. First operation, make heap. In the make heap, we are creating a empty heap having no trees. Okay, no order will be followed. The complexity, worst case complexity for make heap operation, that is our empty heap, is big O 1. Now, as I had already told, when I insert a particular value in the existing Fibonacci heap, again I have to follow no order. Fibonacci heap is allowing us that we can have same order tree in the Fibonacci heap. So, no type of merge or union of order trees will be performed. Okay. So, again we are simply adding a particular node inside the heap. The complexity will be again will be 1, big O 1. I will take an example. You can observe, looking at this particular Fibonacci heap, that it is totally unordered. You are having 2 B0 here. Again the arrangement of B3 is random. One more thing in the Fibonacci heap, that we are having marked nodes that are not in the binomial heap. The meaning of marked node is that particular node had loosened its child. Any node which loses its child, we are supposed to mark it. Now, in the current Fibonacci heap, we are having 3 marked nodes. If I am supposed to calculate potential function for this particular Fibonacci heap, then according to the formula, number of trees present in the Fibonacci heap plus twice the number of marked node present in the Fibonacci heap. So, number of trees present in this given Fibonacci heap is 1, 2, 3, 4, 5. Number of marked node 1, 2 and 3. So, it will be 5 plus 11. The potential function initially it is 11. Again, for the Fibonacci heap, you are having no limitation on the number of trees. It can have any number of trees. While in the binomial heap, we are calculating the number of trees by first converting the number of keys into binary, calculating the where 1 is present, there we are calculating the number of binomial trees which can be present in the given number of keys. While here there is no constraint on the number of trees. So, if there is no constraint on number of trees, again there is no constraint on the height of a tree. So, in this heap, we are supposed to add a particular key. Let I want to add 25. I want to insert this 25 in this binomial heap. After giving a binomial heap, it will be also given to you what is the minimum of this particular heap. This is the minimum for this particular binomial heap. Now, simply when you are supposed to insert a particular value, just consider this value as a heap. This is one heap, another this is a Fibonacci heap only having one binomial tree. The minimum of this particular Fibonacci heap is 25 itself. Let it be a H1. Now you have to insert this node in this, just combine it with or add it with